In today's notes, we're going to take a look at some properties of higher degree polynomials. There are going to be 5 things that we're going to talk about. We're going to explore the concept of local maximums and minimums and extreme maximums and minimums. So our extreme values would be our absolute maximums and minimums. So that's the term that you're going to hear when we're talking about extreme values. And then we're also going to talk about the end behavior of polynomial functions and how to determine what these end behaviors would look like. So here's what we're going to start with. We're going to start with this warm-up. It says, what are the x-intercepts of f of x? So if we're looking at these x-intercepts, we could tell by looking at each of these factors, we'd set them equal to 0 and find out that our x-intercepts are x equals -3, x equals 5, and x equals 4. And then it says, what is the y-intercept of f of x? So remember, the y-intercept is the value when x equals 0. So the quick way to find the y-intercept at any time is just to plug in x equals 0. So you have 2 times 0 plus 3 times 5 minus 0 times 0 minus 4 squared. So I give you 2 times 3 times 5 times 16. And so if you take that, you're going to have 2 times 15 times 16. So your y-intercept would be a point 0,480. And then it says, what is the leading coefficient? The leading coefficient is where you take the coefficient of each x value and the number out front. So you're going to have 2, and then you have 1x, so that's just 1. Then you have -1x, so that's -1. You have +1 squared. And so that's going to be 2 times 1 times -1 times 1, which is just going to be -2. So your leading coefficient is -2. It says, what are the roots of f of x? So those are going to be the same as your x-intercepts. You have x equals -3, 5, and 4. And how many roots should f of x have? So f of x should have 4 roots, because it is a 4th degree function. And so what we'll eventually learn about this in this lesson, not today but tomorrow, is that this root is a repeated root, and so it counts as 2. So if we were going to take a look at how to draw this or sketch this graph, we'd have to make sure we put our x-intercepts on there. So -3, 5, and 4. So we'd have -3, and then 4 and 5. And our y-intercept would be 480, so somewhere way up here. Again, this is just a sketch. And so we'd look at this and we'd see that it would look something like this. So also, if we want to know what degree this is, this would be a 1, 2, 3, 4th degree function. So it would look something like this. Okay, and we'll talk more about how you know what that is doing right there on Wednesday. So as we start our exploration of how to describe different polynomial functions, the first thing we're going to take a look at are our maximums and minimums. So there's 2 different types of maximums and minimums. A function can have a relative or local maximum and a relative or local minimum. And so you'll hear me use the word local or relative interchangeably. A function has a relative maximum if there exists an open interval about such that f of a is greater than f of x for all x in the open interval. Okay, so what does that mean? If we're looking at this picture here, this first picture, you have a local minimum there because that function value, that y value, is lower than all the points around it. So this is going to be a local minimum. You have these other 2 points here that are local maximums because they are bigger than all the other points that are directly around them. So they're at the top of a hill, okay? And then you also have, and think of the local minimum is going to be at the, like in a valley. It's going to be at the bottom of a hill. So again, you have local maximums and minimums, and those are going to be points that the y value is higher or lower than the points directly around it. You also have an absolute maximum, and an absolute maximum is going to be a function value where that y value is bigger than every point, every other y value in the function. And the same with an absolute minimum. An absolute minimum is going to be where you have a point that is lower than every other point on that graph. So if you look at the same graph here, you'll notice that we have a global maximum there. That point is higher than every other point on this graph. If you look at it and draw a line through it like that, you would notice that there is no other point on this graph that it goes higher than that. So that is a global maximum. However, if you look at the other ones, this is a local maximum because it's higher than all the points around it, but it's not the highest. Again, a global or absolute maximum means it's the absolute highest point in this picture. And then this right here is just a local minimum because it's lower than all the points around it, but it's not the lowest. It's not the absolute lowest point, because if you look at this function is going down. And so there's even right here, there's a point that is lower than this point right here. And so in this function right here, there is no global or absolute minimum because the function continues going down on both sides. So let's take a look at this function and describe our absolute minimums and maximums and or our local minimums and maximums. So it says, what degree polynomial is the function at least? How do you know? So again, in order to tell what our degree is for this function, we would take a look at our x-intercepts. You have 1 x-intercept, 2 x-intercepts, 3 x-intercepts, and 4 x-intercepts. So because there's 4 x-intercepts, we know that this is going to be a function of at least degree 4. And that's because there are 4 x-intercepts. We then need to find the absolute maximum value. So if we take a look at this function, you'll see that there's like the top of a hill right here. But that point is not higher than all the other points. You notice when you're looking at this, you have points that are over here or over here that are higher than that point. So because that point is not the absolute highest point on this graph, meaning it does not have the absolute highest y value, this is not going to be an absolute maximum. And in fact, in this case, there are going to be no absolute maximums because this function continues up forever. So because this function on either side, left or right, is going up forever, there's always going to be a point that's higher than the next point. So what we would say is there are no absolute maximum values. So no absolute maximums. And then the next question is, are there any relative maximums? So what you need to understand here is that there can be relative maximums even if there are not absolute maximums. And so this point right here, where it's at the top of this hill, this is a relative maximum. And that is because if you look at the y values directly by that point has a higher y value than all of these other points over here. So it means that it is going to have a relative maximum there. So our relative maximum would be negative 0.562, comma 17.754. And so for us right now, we will have to use the graphs in order to find these maximums and minimums. The next question says, what is the absolute minimum? And so if you look at this, you start looking to see, are there any minimums, any points that are at like the bottom of a valley, and you have a minimum here, and then you have a valley right there. So if you look at this, only one of these is your absolute minimum. So this right here is going to be your absolute minimum because it is the lowest point. If we were to draw a line that passed through that point, you would notice that there are no other points below there. So our absolute minimum would be at the point negative 3.871. comma, negative 35.349. And then for our relative minimum and maximum, both of these are going to be relative minimums. So here, what you need to understand is all absolute minimums are also relative minimums, but not all relative minimums are absolute minimums. So our relative minimums are going to be this point as well, but also 2.183 comma, negative 14.52. Okay, so both of those are going to be relative minimums. For the domain and range here, the domain for these functions is going to be negative infinity to infinity. And then the range here, we would take a look at this and you'd notice that, okay, there is a point that is, when you have an absolute minimum, that is going to be your lowest absolute point. So that lowest y value is going to be negative 35.349. And we're going to go up to infinity. And so then the next question, and what we're going to focus on here for the rest of the notes, is determining the end behavior. So when we have a graph here, it's easy to figure out what the end behavior is. Remember, the end behavior describes what is happening as the x values get really, really small or get really, really big. So if you look at this, you have your left end behavior, which is shown to us right there, and then you have your right end behavior, which is shown to us over here. So in this case, we would say as x approaches negative infinity, so as we go this way on our graph, in the long run, what happens to our y values? In the long run, they end up going up to positive infinity. So our y values are approaching positive infinity. So this is going to be our left end behavior. And then our right end behavior would be as x approaches positive infinity. So as our x values get very, very large, what's happening to our y values? They're also going up to infinity. So we have our end behavior like this. And so our goal for the rest of the lesson is going to be able to come up with a way to figure out the end behavior even when we don't have the graph. So if we just have the equation, how do we figure out what the ends of the function are doing? And so again, just as a reminder, as we work through this lesson, our goals for this first day are that we can determine where the y-intercept is, that we can determine where the x-intercepts are, that we can determine and describe where the local maximums or minimums are, and for us to be able to determine what the end behaviors are. That is our goal for this first day's lesson. And so just as a reminder from what we said up there, the end behavior or long-run behavior of a polynomial is what happens to f of x as x takes on extreme positive and negative values. So what we're going to do is we're going to take a quick look at these four equations here, and we're going to come up with a way to figure out what the end behavior of any polynomial function is going to be based on the leading coefficient and degree of the function. So what I did is I've already filled this in, but to show you what these functions look like, I'm going to bounce back and forth between Desmos. So this is the first function that we have right here. Let's see if I can just do this. So in this first function, 2x to the fifth plus 2x squared minus 5x minus 4, you can see it looks like this. And so this function here, it is in a fifth degree function. It is that, so that degree is an odd number, and the leading coefficient is 2. And as you can see here, as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y also approaches positive infinity. And then if we look at this other function here, the next one, you have negative 3x to the third power plus 5x minus 2. It is a third degree function. So that degree is an odd number. Your leading coefficient is negative 3, and as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches negative infinity. So as your x values are getting smaller, your y values are going up, and as your x values are getting bigger, your y values are going down. If you look at this function, you have a fourth degree function, which is an even degree because it 4 is an even number. The leading coefficient is 5. And when you look at this, you can see that the left and right end behaviors are the same. So as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches positive infinity. And then finally, you have your last one, negative 4x to the 6th plus 2x to the 5th minus 5x plus 3. That is a 6th degree function. It's an even function, even degree function. The leading coefficient is negative 4, and as the x and y values, or as the x values get smaller and bigger, both the y values get smaller on each of those. So what we have here is, you'll notice I labeled these degrees as being an odd degree function versus an even degree function. That's going to help us figure out what the end behaviors are, and so are the leading coefficients. So what I want you to see here is the leading coefficient is going to tell you the right end behavior. Okay, so when you look at this, if you look at the leading coefficient here, this is a positive 2. And if you go look at my right end behavior, you'll notice that the y values are approaching positive infinity. Then if you look at this right here, if the leading coefficient is positive 5, the y values are approaching positive infinity. And then if you look at these ones over here, this negative 3, when you have a negative leading coefficient, your y values on the right are approaching negative infinity. You have a negative leading coefficient, the y values are approaching negative infinity. So what you're able to figure out is just by looking at the leading coefficient, you can determine what the right end behavior is for the function. So when you're looking at this, you'll see in this little chart, when you have a positive leading coefficient, you have a positive end behavior on the right. So as x approaches positive infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity. So the first thing you notice here is that you have this relationship between the sign of the leading coefficient and the right end behavior. When your leading coefficient is negative, you'll notice that the right end behavior is negative infinity. Same thing here. As x approaches positive infinity, y approaches negative infinity. So the leading coefficient is telling you what your right end behavior is. Then the next question is, how do you figure out the left end behavior? And so when you look at this, you'll notice when you have an even degree function, so when you have 4 and 6, you'll notice that the left end behavior and right end behaviors are the same. What do I mean by that? As x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity. Same thing here. When you have a degree that's 6 or an even number, you have, in this case, x approaching negative infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches negative infinity. So again, what you'll notice here is when you have an even degree function, the end behaviors are the same. And I always remember that in the sense that if you're in a race and you're even with someone, that means you're at the same point. So you're in the same direction, okay? So if you have an even degree function, your end behaviors are the same. If you have an odd degree function, though, you'll notice that your end behaviors are different. So we have here a 5th degree function. It's an odd number. And so our leading coefficient was 2, which told us that as on the right, as x approaches positive infinity, y approaches positive infinity. But because we have a odd degree function, on the left, as x approaches negative infinity, y approaches negative infinity. And then same thing here, we have an odd degree function. We had a negative leading coefficient, so that tells us as x approaches positive infinity, y approaches negative infinity, because the leading coefficient tells us our right end behavior. And so since this is an odd degree function, the left end behavior will be different. And so the way that I always remembered it is like if something is odd, that means it's different. So a degree that's odd means that the end behaviors are different. Okay, and so you have this little chart here. And so what you'll see is that if I'm asking you what the end behavior is of a function, there's two things that you need to figure out. You need to figure out what the leading coefficient is. That will end up telling you your right end behavior. And then you need to figure out your degree, because that will tell you whether or not the end behaviors are the same or different. So when you're looking at these end behaviors, really what you're looking at is you're just looking at the first term. So you're looking at the term that has the highest exponent and highest degree. So you're always looking for your term that has the highest exponent. And what that's telling you is that any polynomial, the end behavior is going to be determined by the long run behavior of the polynomial's leading term. Okay. So what we'll do here is we'll look at these three examples, and then we'll call that a day, and you can begin working on your homework. So in this case, what you'll notice here, two things that you need to know. What's the degree, and what's the leading coefficient? So the degree is 18. That's an even number. What does that tell you? The end behaviors, I'm going to abbreviate end behaviors as EB, are the same. Okay, the leading coefficient is equal to -3. What does that tell you? The right end behavior is negative, so it's going down. So what we have here is, I like to write my right end behavior first. As x approaches positive infinity, y approaches negative infinity. Again, because my leading coefficient is negative, my right end behavior would be approaching a negative infinity. And then my left end behavior, as x approaches negative infinity, it's also going to approach negative infinity, because since the degree is even, the end behaviors are the same. So y approaches negative infinity as well. Again, you're looking at the degree and leading coefficient for all of these to determine your end behavior. If you look at this function here, it's not written in standard form, so you would need to find your degree and your leading coefficient. So the highest exponent is 17, which tells us our leading coefficient is 2/3. So we have a degree that is 17. That's odd. And then we have a leading coefficient that's equal to 2/3. And that's positive 2/3. So if we were going to write our end behavior, we would know that our right end behavior, as x approaches positive infinity, is going to be equal to the same sign as our leading coefficient. So since it's positive, the y values are approaching positive infinity. And because the degree is odd, that means the end behaviors are different. Again, think about, if something smells odd, that means it smells different. If something is odd, it's different. So we'd say as x approaches negative infinity, my y values are approaching negative infinity. And then for this last one, it's a little bit hidden here. So you need to figure out your degree. So our degree here would be, you have an x squared, x to the first, and an x. So that's going to be 2, 1, and 1. That means our degree is 4. Our leading coefficient is going to be -1. Oops. So our leading coefficient is going to be -1, 2, and another -1. So you have -1 times 2 times -1. That's going to be equal to 2. So our leading coefficient is just positive 2. And so again, since our leading coefficient is positive, we now know our right end behavior as x approaches positive infinity is also going to be positive. And because our degree is even, that means we know that the end behaviors are going to be the same. So as x approaches negative infinity, y approaches positive infinity. So again, when you're figuring these, when I'm asking you to figure out what the end behavior is, the questions that you should be asking yourself first are, what is the leading coefficient? Because this tells you your right end behavior. And then after you know your right end behavior, you use the degree. If it's an even degree function, you know the y values are approaching the same thing. If it's an odd degree function, you know that the end behaviors are approaching different things. So that is the end of the notes for today. I should be back in class tomorrow to answer any questions. Please work on the homework now so that you can get a jump start on that and come to class with questions tomorrow.